today I will be talking about the divisibility of the class numbers in imaginary quadratic fields. Before I start, I just want to set my notations. So, K is actually number field and the OK is the numbering of number field, and the Jk is set of all fractional ideals. Though I do not use it, I just wrote it to define the class group. So, once it is a set of all fractional ideals, Jk forms a group with ideal multiplication as a binary operation, and we know that the principal fractional ideals forms a subgroup, and when you take a quotient group, that is actually called class group, and it is a very much celebrated result that the class group is it's a finite group and it is actually finite abelian group. It is denoted by Ck, and the order of class group is denoted by Hk, and we call it a class number, and it is a class number is one if and only if the OK is PID. So, when you talk about class number, it is essential to mention about the contributions of Gauss. So, the class number was first appeared in Gauss is book written in 1801, and he also this came up when he is studying the binary quadratic fields, binary quadratic forms, and he also conjectured the following things. So, first one was he conjectured that there is infinitely many real quadratic fields of class number 1, which is still remains open, and then the other one is there exist infinitely many real quadratic fields of the form q root p whose class number is actually 3, even where the p is congruent to 1 mod 4, even this remains open. And the other one is actually conjectured is there exists finitely many imaginary quadratic field class number 1. In fact, he actually also gave a list of those, and this was proved by Alan Baker and Egner and Stark in they proved independently in 1966. Yeah. So, okay. So why do I have to study the divisibility of class numbers? So how does it help me? So, of course, we might be knowing this regular primes, which they give a like knowing the class numbers of cyclotomic zeta functions, that they gave a easy proof of Fermat's last theorem for the regular primes and all. But I will just give some baby example where knowing the divisibility of class numbers is can be used to give a so like to show that some equation does not have a Z solutions. The Diophantine equation does not have Z solutions. So, let me start with this is interesting for two reasons, because it has infinitely many q solutions, and also it has a solution modulo every m greater than or equal to 1. Okay. So, let me consider this quadratic field q 51, because it's there I can see. So, this is the number ring, and it has this is the number ring, and this you can actually see by says that the class number actually is 2, you can easily compute. And so, this actually what I did is actually I wrote I rewrote the equation as x cube is equal to y square minus 51 plus 51, and you can see that these two are the factors that come up in that equation, and yeah, this is what. So, if you see, once I have these two are relatively prime, and if I consider this as an ideal equation, so I can easily see that both the ideals have their relative prime and their product is actually some ideal power cube. So, both has to be some ideal power cube for both both the ideals generated by these two elements. So, now the class number comes into picture. See, what actually I am saying is that suppose if I consider these ideals I and j are ideals of in the elements of the class group, what I am saying is the power ideal, that particular element power 3 is giving me the identity. So, the order should be divisible by 3, but I computed the class from class it says that the class number is 2, which says the order is actually 2, which implies each element has to be the identity. So, which is essentially saying that both the ideals are principal, and if I take the both ideals generated by A and B, and now since there are only 2 units in imaginary quadratic fields, however, I can write this. Yeah, this is y plus root minus 51 is a cube u, and this I can write this way. But we know the units of OK is minus 1 and 1. Using that, we can write y plus 1 plus 2 alpha. Alpha is this one, where 1 plus root minus 51 by 2, I can write this equation, which is equal to a cube, and if I take a to be any element of the number ring, if I write it like r plus s alpha whole cube, if I expand, I will have this equation, this particular thing. But I know that 1 comma alpha is they are actually basis of OK as z basis. So what I have is this thing has to be equal to the coefficients of alpha, which is actually not possible, which is essentially telling that 3 divides 2, which is not possible. So you can actually see that the important step is actually knowing the class number is actually 2. So that is how knowing the divisible properties of class number is useful. Okay, so getting into the history. So in 1922, I think this is the first one. This is the first result appeared about the divisibility of class numbers. So what Nagel proved is that given an odd number n, he proved that there exists infinite family whose class number is actually divisible by n. And 1955, Anki and Chawla, they also produced an infinite family whose class number is divisible by n. They have some certain conditions on x and n. And this is This is in the 1978, Gross and Orlovich. This result is really important. This is another result, which is they have actually no conditions on u. They just have that the given n, if you consider any u greater than 1, n divides the class number of q adjoint root of 1 minus 4 u power n. So actually they use some some geometric techniques, but later on Stephen Lobottini gave a easy proof of using the algebraic number theory, just basic algebraic number theory. So I am just listing few, but actually there are a lot more results on divisibility of class numbers, which I am just ignoring for the time constraint. But there is also this quantitative approach to this divisibility. So Cohen and Lenstra, they predicts that the class number is divisible by n. Like if I take D, they have actually positive density among all the quadratic fields. So if I define this nn of x, which is actually set of all d such that n divides the class number of q adjoint root d. Okay, this is a typo. This is q root d, and d less than or equal to x. Actually, Cohen-Lenstra heuristic predicts that this nn of x is actually asymptotically equal to Cn of x, where Cn is some constant, and they also have written down the explicit expression for Cp, where p is a prime. And some of the notable ones are actually Ramurthy has proved that nn of x is actually greater than or equal to x power n 1 by n minus epsilon under ABC conjecture. And later on he proved that it is actually nn of this is x power 1 by 2 plus 1 by n. And Soundarajan actually improved it later, and I think up to now I think this is the best known bound, and there may be some in special cases, but in general this is seem to be the bound known. Yeah, so let's stick to the one family of imaginary quadratic fields, which are of the form q adjoint 1 minus mu x power n. This is a family, and okay, so for mu is equal to 4, it was proved by Gross and Orlovich, and as I said, I also mentioned this is the proof. This is where the Stephen proof appears, and Ramurthy proved whenever x minus 1 minus x power n is actually square free, he proves that n divides the class number of q adjoint root of 1 minus x power n, and but they so mu is equal to 2 is it was only dealt for mu is equal to 2 and n is equal to 3 by Ajihul and Kalyan, and we actually proved that for mu is equal to 2 and n is equal to any prime, and here there is the x constraint in x is x has to be some prime power. That constraint we got it because of we wanted some Diophantine equations solution. We wanted to prove some Diophantine equation doesn't have a solution, and like it has only few solutions, but that came that we had to have that m has to be some prime power. That is okay. So the people also have studied the simultaneous divisibility of class numbers, and to list few listed this Komastu, he actually proved infinitely many d such that 3 divides q root d and q root md, and Ito she proved that 3 divides there is infinitely many D's such that Q divides this, and she in the same paper she also mentions that there are infinitely many D's such that 3 does not divide the class numbers of this. So now this also comes to as a general result, given any m and n, there exists infinitely many D's such that n divides the class number of Q root D and Q root and also Q root MD. Yeah. So yeah, this is also a result of Aki and Kishi that they also gave an infinite many family for 5, which divides like simultaneous family for 5. And in the same line, Izuka in 2018 he actually gave infinite family of infinitely many D such that 3 divides the class number of Q root D and Q root D plus 1, which is actually you can see the consecutive ones. And after proving this particular thing, he actually conjectured that there exists n simultaneous like successive numbers such that d plus n, such that P divides the class number of these fields where P is any prime. That is what he conjectured, and using the result of Gross, we could actually prove that as a corollary of our theorem, we could prove that this conjecture is true for n is equal to 1. We actually, this is a simple construction that okay, this is what we had, and we just added 4 to that, and power p it still remains same, and then use the choose a certain u and put it into the Gauss theorem and Gross theorem that we get this, and you can see that these two are actually like if I consider this to be D, and they are actually Q root D and D plus 1. Okay. So the present status of the conjecture is actually, so at the moment it is they were able to produce D plus 1 and D plus, with some distances. This is in some sense the first one. After this they produced triple, where other one is like k square, where k is with some conditions. Another one is like D plus 1, D plus 4 and 4 p square, and so there is at the moment there is no result which has a consecutive 3 quadratic fields. Yeah. So I will just give a general procedure how like this class number how they prove that n divides the class number. So given an okay, sorry, it's not fine. Given any n, we construct an element alpha belongs to OK such that the alpha generated, the ideal generated by alpha is actually some ideal power n. So now if I can prove that this ideal is not principal, or it has order not in, you want to prove that I has no order no less than n. For that I need to prove that for any prime p which divides I power n by p is not a principal ideal for any p dividing n. So that is what we want to prove. For this we will claim that what the procedure is, will suppose this is principal, and then we end up something like alpha being some plus or minus beta power p, and the later we prove that alpha plus or minus alpha cannot be actually p power in OK. That is actually the general procedure, and quickly I will just run through 1 minute. Yeah, I will just finish it quickly. So here in my case, let me consider my d to be this, my alpha is actually this 1 plus root of this. If I consider my norm of alpha, it is 2 times m power p, and where my m is actually prime power. So because of that I can say that okay, the ideal by alpha has only 2 prime factors. One is 2, the prime that lie above 2 and the prime lie above q, and so my it will look like this, and then you play with norm, and we want ultimately what we want to prove is that the t is actually like it is of the form Rp, it is a power it divides p, the t is divisible by p. That is what I want to prove. Look at this I power p, it will be like this, and then now what I have is if I assume that I to be principal, then I have beta power p is actually this one. So since I know that the only units of the imaginary quadratic field is plus or minus 1, but instead of p being pth power I have is a bit different, but this still I can proceed the similar way, and I ultimately this comes down to having I'll get some Diophantine equation, and I'll say that I'll get some more than 2 solutions, but there's a result by exponential Diophantine equation which has more than 2 solutions, but the result by Shore and others that it has only 1 solution. Using that I get a contradiction. Yeah, thanks. These are the results, and thank you. Anyway, once again, happy birthday to you.
It's not a question, it's just the fact that Wegener indeed proved the Gauss result in 52.
Oh, okay.
In the 60s. But it was not considered as being correct for a long time, because he was quoting some book by Weber in which it was known that there were parts which were not correct, but indeed he was not using the part which was not correct. But this has been understood only and looked again back in the after 65, after he passed away in 65, unfortunately.